super job, you guys. Hey, did you know that NASA is working with students to develop new products and new experiments for space research? Dr. John Poyman, a professor of chemistry and biochemistry at the University of Southern Mississippi, has some cool applications for microgravity research, which students just like you can be working on someday.
What is buoyancy-induced convection?
What is the relationship between density and volume?
What is the trend in the density versus temperature graph?
Hi. NASA's Reduced Gravity program began in 1959, but in the past 5 years, students from over 100 schools have performed experiments in a microgravity environment. Several of my students and I have flown on the KC-135, NASA's flying laboratory. It's science that's interesting, challenging, and fun. One experiment we are conducting involves making new space-age materials by a really cool process called frontal polymerization, and the other involves studying how molecules attract each other in fluids that mix. Everything is made up of very, very small pieces of stuff called molecules. Molecules attract each other. How strongly they attract determines if the stuff is a liquid, solid, or a gas. Some materials mix completely, others do not. Here's something you can try at home yourself. We have water here, which has food coloring in it, and syrup. And as I pour the syrup in and stir it up, it'll make one continuous liquid. But if I take something that's immiscible with water, like mineral oil, and pour it into the water with food coloring, and mix this solution up, it will separate into two layers with time. Water molecules attract each other more strongly than they attract oil molecules, and so the water stays separate. A monomer is a small molecule that can be made to form long chains of monomers connected end to end, called a polymer. It's sort of like boxcars hooked together to form a train. The mixing process is called convection. It's the term for liquid motion. There are two ways in which convection can spontaneously occur in a liquid. One is caused by gravity and is called buoyancy-induced convection. Differences between the densities of the liquids make the lighter fluid rise and separate from the heavier fluid. Another type of convection is called interfacial tension-induced convection.
Interfacial what?
Interfacial tension-induced convection. Let's split the term up. First, interfacial tension is like the surface tension, which holds up a water bug when it skitters across a pond. The surface is the result of the water molecules attracting each other. But heating a surface here on Earth causes buoyancy-induced convection. How can we study only the convection caused by interfacial effects alone? We need to eliminate gravity or its effects. We can never eliminate gravity, but by free-falling we can create a system that acts as if there were no gravity. Performing experiments in weightlessness allows us to study phenomena we can't study on Earth, and to answer questions we can't answer down here. By eliminating buoyancy-induced convection, we sometimes can create superior protein crystals in weightlessness that can help researchers design new drugs. Eliminating buoyancy-induced convection can also help us understand how to make better semiconductors here on Earth, like the ones used in your computer. We take a lesson from computer chip manufacturers who use light to make the circuit patterns. Microgravity research shows us that we can create patterns on fluids which would not be allowed on Earth, where buoyancy convection mixes up the patterns due to gravity. My students and I are studying how forces between molecules in fluids that mix can cause convection. We use light as an initiating agent to make the monomer turn into the polymer. By exposing the monomer to light with a specific pattern, we hope to observe how the monomer and polymer molecules pull on each other. For many minutes, we predict that the two fluids will act like oil on water. But in the long run, the molecules will diffuse into each other and make a single fluid. Why can't we do the experiment in the lab? Because buoyancy-driven convection will smear everything out. So there really is no way on Earth to do the experiment. We also study a process called frontal polymerization, in which plastics and foams can be made with a chemical reaction that spreads out like a liquid flame. Gases can be released by the hot reaction that makes bubbles, which can form the foam. Of course, bubbles float in a liquid because of gravity. But without the buoyant force, bubbles can become larger in a microgravity environment.
How do you use math in your work?
Math is essential to our work. For example, in order to predict how gravity will cause convection in our systems, we need to prepare graphs of the density of our materials as a function of temperature. We use a special instrument called a densitometer. But we have to know how to use the math to make sense of what it tells us. Let's look at some of the data from my lab. Here we have plotted the densities of the monomer and the polymer on the y-axis and the temperature on the x-axis. First, notice that the density of the polymer is higher than the monomer. Next, we can draw straight lines through the points. The slope of each line is the ratio of the change in density to the change in temperature. The density of the polymer decreases 0.03 grams per cubic centimeters for a 50 degrees centigrade increase in temperature. The density of the monomer also decreases, but it decreases 0.04 grams per cubic centimeter for the same temperature change.
Remember that we said buoyancy-driven convection happens because of differences in density, and that the less dense liquids will float to the top. And information from this graph tells us how the density changes when we heat the monomer and polymer, and so we can predict how much buoyancy-driven convection will occur during experiments on Earth. The graph also tells us how much the volume changes as we heat the liquids, essential information for designing our experiment on the International Space Station.
As we go farther and farther from Earth into space, we're going to be required eventually to make our own materials in space. Foams are just one of the things we need to look at. Gaining an understanding of the opportunities in microgravity research today will be valuable knowledge for you, the young researchers of tomorrow, when we are ready for our first manned flight to Mars.